Welcome everybody once again. So we are in our fifth module, and in the last class, that is in part 1, we saw one example how to analyze a curved beam which forms a quadrant of a circle. In other words, a cantilever curved beam forming a quadrant of a circle and subjected to a concentrated load at the free end. Now in today's class we are going to see another example of a curved beam, a cantilever curved beam forming a quadrant of a circle, and it is subjected to uniformly distributed load. So today we are going to analyze a cantilever curved beam forming a quadrant of a circle and subjected to UDL, uniformly distributed load. So let us see how to analyze this problem. So our problem is a curved beam AB of uniform cross section is horizontal in plan and is in the form of a quadrant of a circle of radius R. The beam is fixed at A and free at B. It carries a UDL of W per unit run over the entire length of the beam as shown in figure. Calculate the shear force, bending moment and torsional moment values at A and B and sketch the variations of the same. Also determine the deflection at the free end B. So we need to find the shear force, the bending moment, the twisting moment, their variations and the deflections. So our given diagram or the given beam, given curved cantilever beam forming a quadrant of the circle is like this. So one end is fixed. So end A is fixed and end B is free. So we can take this as A and this end as B. So if you extend A and B perpendicularly, this A and B will meet at a point. We will take this point as O. If you keep O as radius, O as center and radius equal to OA or OB. OA is radius, OB is radius. If you draw, you can get a circle. And this beam AB, it forms a quadrant of a circle. Now, this AB is subjected to a uniformly distributed load. Uniformly distributed load of W per unit run. Now, we need to analyze this beam. So, how will we analyze this beam? So, for analyzing this beam, since it is a cantilever, this is statically determinate. Okay, so this beam is a statically determinate beam. So now, since it is a cantilever, we will start our analysis from the free end. So after confirming it is statically determinate, we will move on to step 1. So step 1, we will find the shear forces. We are going to analyze the shear force. So for analyzing the shear force, we will consider a section X at some point in the span AB. So we will draw the beam AB. Okay, I will draw the beam here. This is our beam, right? So fixed beam A and B. This is O, radius R, radius R. Now let us consider a section X. So we will consider a section X. Okay. This is the section X and this section Let this section makes an angle of theta with OB. And we know there is UDL, right? There is UDL. Now, when we are taking the shear force, we know shear force is the summation of all the forces either to the left of the section or to the right of the section. And when you are taking a section, the left upwards and the right downwards is positive. Now, when you are taking X, these loads are downward loads. So, right downwards becomes positive. Okay. So, this is independent of theta. Sorry, this is not independent of theta because this is the summation of all the loads to the right of the section. So, when you take section X, so at X, your shear force F theta will be equal to, this loading is W, intensity W per unit run. So, this distance is R into theta, because this is R, this OX is R. So, this distance, okay, so this distance becomes R into theta. That means at X, if you take summation of all the forces to the right of X, load is W into, this is UDL, right? So, the distance is R into theta. See, from this formula, we can understand that shear force depends on theta. W is constant, W per unit run is constant, radius is constant. So, theta is varying. So, at B, theta is equal to 0. If theta is 0, our shear force F theta is equal to 0. Shear force is equal to 0. At A, theta is equal to 90 degree, right? This is 90 degree. So, at A, theta becomes 90 degree. Therefore, our shear force F theta becomes W R into pi by 2. Because theta is pi by 2, that is nothing, 90 degree is nothing but pi by 2, right? So, F theta is equal to W R pi by 2. So, this is nothing but pi W R by 2. Pi W R by 2. So, now we can draw the shear force variations. Shear force at X it is W R theta, at B it is 0, at A it is pi W R by 2, everywhere it is positive. So, now we will draw the variations of shear force. Okay. So, this is A, this is B. We can join this O. Let this point be X, section X. So, at A, at B, the shear forces is 0, right? Now, we will draw the shear force diagram. At B, shear force variations. So, at B, shear forces is 0. At X, shear forces W R theta. So, here we have this is W R theta. At A, pi by 2 W R, pi W R by 2. At A, it is pi W R by 2. So by drawing the variations, we will get at B, it is 0. Okay, so everywhere it is positive. So it is X at X. This distance is WO. R theta. Okay. See, this is actually curved, not the straight line. This is a curved line. Now we will move on to our second step. Our second step is obtaining the bending moment, right? Step 2. Step 2, we will analyze for the bending moment. So bending moment, we know moment of a section is nothing but the force into perpendicular distance. But here it is subjected to UDL. Okay, if it is a concentrated load, it is load into perpendicular distance. Load into perpendicular distance. If it is a UDL, again load into the perpendicular distance. So how will we obtain this for this case? So here we will consider a small stripe of a section in the beam. Okay, so let us take that a stripe. We will take, see, this is from B, at this distance we are taking X. So in this portion, because for a cantilever we will be always analyzing from the free end. We will start the analysis from the free end. So in this portion we will consider a small stripe. Okay, let us consider a small stripe in this section. So let us imagine that this stripe makes an angle of d theta with O. So this angle is d theta. Okay, if this angle is d theta, this distance will be equal to r into d theta. Sorry, we will take this as theta. Okay. We will take, sorry, we don't take it as theta because theta is the angle measured from OB. So we will take this as pi. Otherwise, it will develop some confusion. So we will take this as pi. So this distance will be equal to, see, this distance is S and this S is equal to R into d pi. Now, for this smaller stripe, we will draw from this point, from the center point of the UDL of this smaller stripe, we will draw perpendiculars. We will draw perpendicular from this towards this section. So this is 90 degree. Okay, we will take this point. This is X. This is X. So this O, we will take this as, this point is D, this point is E, and this, okay, this point is X. Okay, so we will draw DE perpendicular to OX. So now our bending moment will be equal to this load in this stripe multiplied by DE into perpendicular distance DE, and the twisting moment will be equal to load in this stripe multiplied by the perpendicular load EX. So now for the bending moment, as I told you in the last class for the previous problem, when you are considering the bending moment for a section, the right clockwise becomes negative. Right clockwise and left, sorry, right clockwise and left anti-clockwise becomes negative. Here, the load of the stripe is to the right of the section. So downwards, so bending moment is negative. So what we get is bending moment on this smaller stripe. So dm theta, bending moment on the smaller stripe is equal to load. Load is, the intensity of the load is W multiplied by the distance, this distance, because it is UDL. So R into d pi. Now the load is over, multiplied by the perpendicular distance. Perpendicular distance is ED. Okay. ED. Now, see this angle I told you, for this smaller stripe the angle is taken as pi, and for this angle can be taken as, this is smaller, the angle subtended by this smaller stripe at O is d pi, and this angle, see this angle is taken as pi. So you take triangle EOD. You will get ED is equal to R sine pi. So we get WR d pi into R sine pi. So now from this we will find what is m theta, the bending moment with respect to theta. So m theta will be equal to, now we can differentiate this from 0 to theta, because you can see here x, the section x subtends an angle theta with OB. So the variation is from 0 to, the angle is varied from 0 to theta. From 0 to theta. So m theta is equal to, that is m theta means the bending moment at section x is equal to minus, see it is the summation of bending moment at x, means the summation of all the bending moment to the right of x. That is why we are taking the integration from this b to x. Since we are taking with respect to the angle, it is from 0 to theta. So it is minus, see already we have minus here, because right clockwise is negative. There you will have hogging moment, so it is negative. So minus integration of 0 to theta WR d pi into R sine pi. So we get minus, you have WR R, so you can take minus WR square outside. 0 to theta d pi, can write it as sine pi into d pi. So integrating we get this is equal to minus WR square, integration of sine pi is minus cos pi. So minus cos pi 0 to theta. So we get minus WR square into minus cos theta plus cos 0. So cos 0 is equal to 1. So we get m theta is equal to minus WR square into 1 minus cos theta. This is our bending moment for the section X. Bending moment at the section X. This is the derivation for the bending moment at section X for a curved quadrant beam when subjected to a uniformly distributed load. Now this varies with respect to theta. So now we can take theta when theta varies from 0 to 90, that is 0 to pi by 2. At B, theta is 0. At A, theta is pi by 2. So at B, theta is equal to 0. Our bending moment will be equal to m theta, or m bending moment at B will be equal to minus WR square into 1 minus cos 0. So cos 0 is equal to 1. So we get 0. 1 minus 1, 0. At A, theta is equal to pi by 2. We get m theta is equal to minus WR square into 1 minus cos pi by 2. Cos pi by 2, cos 90 is, cos pi by 2 is 0. So we get minus WR square. We get minus WR square. So that's all the bending moment. Now we will draw the variations of the bending moment. At B it is 0. At A it is minus WR square. So this is our shear force diagram. Now we will draw the bending moment diagram. This is A, this is B, this is O. So we know for the bending moment diagram at B, bending moment is equal to 0, and at A, bending moment is equal to W minus WR square. So this is minus WR square. So it is minus, okay, you can write here WR square and mention here it is minus, or you can put minus WR square. So at A it is minus WR square, at B it is 0. This is our bending moment diagram. Anyway, we will remove this minus. Okay, this is understood. Now we will move on to our step 3. Step 3 is torsional moment at section X. So step 3, I will write it here. So step 3 is torsional moment. So torsional moment, it is the it is this load in this smaller stripe multiplied by Ex. Okay, this distance Ex. So similar to our bending moment, torsional moment, that is dt theta will be equal to minus W into R d pi. This is our load multiplied by, instead of ED, torsional moment is due to Ex. So it is Ex. Now when you take Ex is equal to R minus OE. So when you take triangle OED, we get Ex is equal to R minus, the value of OE is R cos phi. So we get Ex is equal to R into 1 minus cos pi. We will substitute. This is equal to minus WR d pi into R into 1 minus cos pi. So now t theta is equal to, we can integrate it from 0 to theta. So minus is taken outside. So WR d pi into R into 1 minus cos pi. That is equal to, we can take minus W, this R into R square out. We get integration of 0 to theta 1 minus cos pi into d pi. So that is minus WR square into integrating 1 into 1, integration of 1 is pi minus integration of cos pi is sin pi. Zero to theta. So we get minus WR square into theta minus sin theta. When you substitute 0, sin 0 is 0. So this is t theta. This is our twisting moment for section X. Twisting moment for section X. Now we can see at theta is equal to 0. That is at B. Right? At B, theta is equal to 0. We get t theta is equal to, theta is 0. Sin theta, sin 0 is 0. So we get 0. At A, theta is equal to pi by 2. We get t theta is equal to minus WR square into pi by 2 minus sin pi by 2. Sin pi by 2 is 1. So we get t theta is equal to minus WR square into pi by 2 minus 1. So the torsional moment varies from 0 at the free end, 0 at B, to minus WR square into pi by 2 minus 1 at A. So if you substitute the values, value of pi is equal to 3.41, you get minus 0.571 WR square. Now we will mark the variations. We will draw the torsional moment diagram. So bending moment diagram is drawn. We will draw the torsional moment diagram. This is A, this is B, this is O. So torsional moment is, the magnitude at A is 0.571 WR square, and at B it is 0. Everywhere it is negative, right? So it is negative everywhere. So this is your torsional moment diagram. Now our last step, step 4, we will be finding the deflection. Deflection at B. We are asked to find the deflection at the free end B. So that is our step 4. We will find the deflection at the free end. Deflection at the free end. So for finding the deflection at the free end, see the same concept which you have studied in structural analysis 1. We have studied when we need to find the deflection at the free end, we will assume an imaginary load W at the free end. So here also we are going to assume an imaginary load W at the free end. See, there is no load, but we are going to assume an imaginary load of W at the free end. So I think we can draw the diagram once again, because otherwise it will be confusing. So we will take this point as O, section as X, and we will assume a load W is equal to 0 at the free end B. Okay. So now we will use the method of strain energy. We know the deflection at the free end will be equal to dou U by dou W. At this W is equal to 0. Finally, we will substitute W is equal to 0. And we know now U, that strain energy U is equal to integration of m theta square ds by 2EI plus integration of t theta square ds by 2GJ. So that is equal to, this m theta square can be written as m theta into dou m theta. So you can write dou U by dou W. Dou U by dou W as one by EI into integration of m theta into dm theta by dw into ds plus 1 by gj of integration of t theta into d t theta by dw into ds. Okay. Now we will find what is, we know m theta is equal to, that is m theta means moment at section x. We have found in the bending moment, moment at section x is minus w r square into 1 minus cos theta. So moment at section x m theta is equal to minus small w, okay, small w r square into 1 minus cos theta. See, the intensity of load is taken as small w and this concentrated load is taken as capital W. So we get, we are going to find this. Okay. So from this we get dm theta by dw will be equal to, sorry, see this moment is only for the UDL, right? Now we have assumed another concentrated load also, another concentrated load of W. So the moment due to this load is minus W into R sin theta. Why it is R sin theta? We are assuming X So this section is making an angle of theta with the horizontal with OB. We are drawing a perpendicular from B. So this distance, this is load into perpendicular distance. This distance is, this is R sine theta, right? This is R sine theta. And this distance, we will take this as H. Okay, so HB is R sine theta and HX is R into 1 minus cos theta. R into, that is Hx is equal to R minus R cos theta. So we get R into 1 minus cos theta. We will use this for torsional moment. Okay. So m theta is equal to minus WR square into 1 minus cos theta minus WR sin theta. So now we get dm theta by dw is equal to, here there is no, with respect to capital W, right? So this term becomes 0. We have only this term. So we get minus R sine theta. Okay. Now we obtained m theta, dm theta by dw. ds, we know ds is equal to, this is ds. This ds is equal to rd, sorry. We will take a smaller stripe. We will take a smaller stripe, making an angle of d theta. So this distance is ds is equal to r d theta. Now we will find what is the torsional moment at x. We have already found the torsional moment is equal to minus WR square into theta minus sine theta. This is for the UDL. Okay. So we get minus WR square into theta minus sine theta. This is for the UDL. Now for the concentrated load, it is W into R into 1 minus cos theta. W into Hx. So W into R into 1 minus cos theta. So minus W into R into 1 minus cos theta. Now we will substitute. Also we know ds is equal to R into d theta. Now we will substitute these values in this equation. Dou u by dou w. So we get dou u by dou w is equal to 1 by ei into integration of, the integration is from 0 to pi by 2, from b to a. So 0 to pi by 2. So 0 to pi by 2 into m theta. M theta is minus WR square into 1 minus cos theta minus WR sin theta. So m theta multiplied by dm theta by dw, that is minus R sin theta into ds. ds is R into d theta. R into d theta plus plus 1 by Gj into integration of 0 to pi by 2 into t theta into d theta by dt theta by dw. So t theta is minus WR square. Okay, from this we didn't find dou t theta by, okay, we will find that also. Sorry. After finding dt theta by dw, we will come for this dou u by dou w. So first of all, we will find dt theta by dw. This term, see this term is equal to, here there is no w term. We have w term only here. So we get minus r into 1 minus cos theta. Now we will substitute in this equation. Okay, dou u by dou w. So delta is equal to, we know delta at B is equal to dou u by dou w is equal to 1 by EI into integration of m theta. That is from 0 to pi by 2 m theta into dm theta by dw into ds plus integration of 0 to pi by 2 t theta, plus 1 by gj into integration of 0 to pi by 2 t theta into dt theta by dw into ds. So we will substitute, we get delta B is equal to 1 by EI into integration of 0 to pi by 2 m theta. Value for m theta is minus WR square into 1 minus cos theta minus WR sin theta. So we get minus WR square into 1 minus cos theta minus WR sin theta into dm theta by dw is minus r sin theta. Minus r sin theta into ds is r d theta plus 1 by gj into integration of, we'll close, okay, integration of 0 to pi by 2 t theta is, we have found it, t theta is equal to minus WR square into theta minus sin theta minus WR into 1 minus cos theta multiplied by d theta by dw is minus r into 1 minus cos theta into r d theta. ds is r d theta. So this is equal to some mistakes. minus r into 1 minus cos theta. Okay. So this is equal to 1 by ei into integration of 0 to pi by 2 we will take we get minus w r square minus w r square. So plus r into sin theta. It's okay. Oof. We will multiply this minus r square sin theta together. Okay. We will bring this to this. So we get minus into minus plus. So plus w r raised to 4 okay, how to write this? Into 1 minus cos theta into sin theta. See, we have multiplied this with this. Minus into minus plus w r raised to 4 into 1 minus cos theta. So we have multiplied this term with this term. Now we will multiply this term with this term. So we get plus w r cube sin square theta into d theta plus 1 by gj integration of 0 to pi by 2 into we get, so this multiplied by this, we get w r square into theta minus sin theta multiplied by 1 minus cos theta. So you get r cube here, right? R cube or r raised to 4. W into r raised to 4 minus w r square. So plus minus into minus plus. We have multiplied this by this. Okay. So we get plus w r raised to 4 into theta minus sin theta into 1 minus cos theta. Minus, now we will multiply this term with this term. So we get minus into minus plus. So plus W R cube into 1 minus cos theta the whole square into d theta. So that will be equal to, so this is equal to 1 by EI, or we will take R cube outside. R cube is common. So we will take R cube by EI into integration of 0 to pi by 2 W R into we will take this one sin theta also as common. One sin theta as common. So we get one minus cos theta plus W sin theta into d theta plus okay, sorry. We will write this as R cube by EI into integral 0 to pi by 2 WR into 1 into sin theta. That is a sin theta minus sin theta cos theta plus W, R cube is taken out, W sin square theta into d theta. D theta plus, from here we will take R cube out. So R cube by GJ into integration of 0 to pi by 2 into W R theta minus W okay, we will write, we will take WR. So remaining things are R cube is taken out. So remaining things are WR into theta into 1 theta minus theta cos theta minus sin theta plus sin theta cos theta plus, so we will close this, plus R cube is taken out. We have W into A minus B the whole square. This is 1 minus cos theta the whole square. A minus B the whole square. We get 1 minus 2AB. So 2 cos theta plus B square cos square theta into d theta. So from which we get that will be equal to r cube by ei into we are integrating this, we get WR into integration of sin theta is minus cos theta minus or plus when you integrate sin theta cos theta we get half of cos 2 theta by 2 plus W into write sin square theta in terms of sin 2 theta, we get okay. So I will remove this now. See, hope you understood this. R cube by EI into WR, small WR into the integration of sin theta is minus cos theta. Okay, or else we will write it one more step so that will be easy for you. So R cube by EI into integration of 0 to pi by 2 WR into sin theta minus, see sin theta cos theta. We know sin 2 theta is equal to 2 sin theta cos theta. That means sin theta cos theta is equal to sin 2 theta by 2. So we can write this as sin theta cos theta. We can write sin theta cos theta as, so sin theta cos theta is equal to sin 2 theta by 2. So we can write sin theta cos theta as sin 2 theta by 2 plus W into sin square theta. We know sin square theta plus cos square theta is equal to 1. So sin square theta is equal to 1 minus cos square theta. We also know, see, sin square theta plus cos square theta is equal to 1. Also, sin square theta is equal to 1 minus cos 2 theta by 2. So we can write this as 1 by 2 minus cos 2 theta by 2. So we will replace this sin square theta by 1 by 2 minus cos 2 theta by 2 into d theta plus r cube by gj into integration of 0 to pi by 2 into WR into theta minus theta cos theta minus sin theta plus sin theta cos theta. So we know, see, sin theta cos theta, we know sin 2 theta is equal to 2 sin theta cos theta. That means sin theta cos theta is equal to sin 2 theta by 2. So we will replace sin theta cos theta is equal to sin 2 theta by 2. So sin 2 theta by 2 plus W into 1 minus 2 cos theta plus cos square theta is 1 plus cos 2 theta by 2. So 1 plus cos 2 theta by 2, that is 1 by 2 plus cos 2 theta by 2 into d theta. So cos square theta is 1 plus cos 2 theta by 2. That is 1 by 2 plus cos 2 theta by 2. Now we can do the integration. So doing the integration, we get r cube delta b is equal to deflection at b equal to r cube by ei into, when we are integrating, we get WR into integration of sin theta is minus cos theta. Minus cos theta minus 1 by 2 into integration of sin 2 theta is minus cos 2 theta by 2. So we get plus cos 2 theta by 2 plus W into integration of 1 by 2. 1 by 2 is constant. So you get theta by 2 minus cos 2 theta is sin 2 theta by 2. So sin 2 theta by 2 into 2. We get 4. Plus r cube by gj into, so here it is 0 to pi by 2, right? Okay. Into WR into integration of theta is theta square by 2 minus integration of theta cos theta. So it is of the form uv, right? U into dv. This is of the form u into dv. So we get minus theta into sin theta minus cos theta into differentiation of theta is 1. Theta into u into dv. Integration of u into dv is equal to uv minus u1 v1. So u is theta. V is differentiation of cos theta is minus sin theta. Sorry, differentiation of cos theta is minus sin theta. So we get minus theta into sin theta minus u1 v1. u1 integration of theta is 1. Sorry, differentiation of theta is 1 into v1. So how can we write that? Minus theta into cos theta. So u into dv, cos theta into d theta, right? So uv minus u1 v1. U is theta. Integration of so u is theta Differentiating, we get u1 is equal to 1. V integrating, we get sin theta. V1 we get minus cos theta. So minus theta so we get uv minus theta into cos theta plus sin theta. So what is here? Okay, we can take it in the other form. So integration of theta cos theta. So minus theta into cos theta. So we can take this theta as u and cos theta as dv. So what we get is, so I will explain you here, minus of theta into cos theta. You have to integrate minus of theta into cos theta into d theta. So this theta is taken as u, cos theta into d theta is taken as dv, from which we get u1, that is differentiation of theta is equal to 1. From dv we integrate, we get v is equal to integration of cos theta. Integration of cos theta is sin theta. Now v1 integration of sin theta is minus cos theta. So when we integrate we get minus of uv minus u1 v1. So we get minus uv. uv is theta into sin theta minus u1 v1 is minus cos theta. So minus into minus we get plus, plus cos theta. So what we get is minus theta sin theta minus cos theta. Okay. So integration of minus theta cos theta is minus theta sin theta minus cos theta. Okay. So we can write this as minus theta sin theta minus cos theta. Now minus integration of sin theta is minus cos theta. So minus into minus plus, plus cos theta. Now integration of 1 by 2, right? Plus 1 by 2. Integration of sin 2 theta is minus cos 2 theta by 2. So cos 2 theta, this is minus, right? Minus cos 2 theta by 2. Plus w into integration of 1 into d theta is theta minus 2 integration of cos theta is sin theta plus 1 by 2 integration of 1 by 2 is 1 by 2 into theta. So theta by 2 plus integration of 1 by 2 into integration of cos 2 theta is sin 2 theta by 2. So sin 2 theta by 2 0 to pi by 2. So what we get is delta B equal to r cube by EI multiplied by WR into cos pi by 2. That is cos 90. Cos 90 is 0, right? Cos 90 is 0. So cos 90 is 0 minus 0. Cos 0 is 1. So minus into minus plus. So we get 1. See, that is minus cos pi by 2 minus, see, minus of, I'll write like this, minus cos pi by 2 minus cos 0. So this is 0, cos 0 is 1. So we get minus into minus plus 1. Now the next value, it is plus 1 by 2 into 1 by 4. We will take 1 by 4. So plus 1 by 4 into cos 2 theta. So cos 2 into pi by 2 minus cos 0. Cos 0, the value is 1. Cos 180, the value is minus 1. So minus 1, it is minus 2. Minus 2 plus W into theta by 2. Theta is pi by 2. Theta is pi by 2. So pi by 2 into 2. The theta is 0. So pi by 4. So we get pi by 4 minus 1 by 4 into sine 2 theta. Sine 2 into pi by 2 minus sine 0. Sine 0 is 0. Sine pi means sine 180 is also 0. So we get 0. So minus 1 by 4 into 0 plus r cube by gj into WR into theta square, that is pi by 2 the whole square by 2. We get pi square by 8 minus sine pi by 2 is 1, sine 0 is 0. So pi by 2 minus pi by 2 minus cos pi by 2. Cos 90 is 0 minus cos 0 is 1. So we get, okay, minus cos theta plus cos theta get cancelled. So next one is minus 1 by 4 into cos 2 theta, that is cos pi. Cos pi is minus 1, cos 0 is 1. So minus 1, minus 2 plus W into theta pi by 2 minus 2 sine pi by 2. 2 into sine 90 is 1, sine 0 is 0. So 2 into 1 plus theta by 2. So theta is pi by 2, so pi by 4 plus 1 by 2 into 1 by 4 into sine 2 theta. That is sine pi by 2. When you substitute pi by 2, sine pi is 0, sine 0 is 0. So you get 0. So that will be equal to, so delta B equal to R cube by EI multiplied by WR WR minus okay, this is 1 minus 1 by 2. We get 2 minus 1 by 2, it is minus 1 by 2. Sorry, plus 1 by 2. So WR by 2. We get WR by 2 plus, this is 0, pi W by 4 plus R cube by GJ into WR into pi square by 8 minus pi by 2 plus 1 by 2 plus W into 3 pi by 4 minus 2. Now, we know our W, capital W is imaginary. Capital W is equal to 0. So, which implies delta B is equal to W, small w, R power 4 by 2 EI plus this term completely becomes 0. So, we get plus W R cube by GJ into pi minus 2 the whole square. So, this is your answer. This is your value for deflection. So, hope you understood. See, this derivation is a little larger. If you practice it, it will be easy for you. So, we saw how to analyze a cantilever when it is curved in plan and it is subjected to a UDL. You have to draw the shear force degree distribution diagram, bending moment distribution diagram, torsional distribution diagram and the deflection. Okay, deflection is little confusing. If you concentrate, if you practice 2 or 3 times, you will be getting the answer. So, thank you.